So continuing with our Venn diagrams and unions and intersections, we have this addition rule. So what we're going to look at is, this is something that you will be given. The addition rule states that the probability of the union of two events occurring is just the probability of one event occurring plus the probability of the other event occurring minus the probability of their intersection. The reason we have to subtract out the intersection is that's included in both of these. So therefore we can't add it twice. So that's why we subtract out that overlap, because again, it's counted in both. So not only is this going to help us as we're calculating probability types of questions, but this formula is also going to come up, because sometimes you're going to do a problem and they're going to give you some crazy formulas, such as in example 4. And you're like, I don't know how to find that, but you do know parts of it, so you can substitute things in and start to use it. Here's what I mean by that. So in example 4, we have events A and B happening. We know the probability of A occurring, we know the probability of B occurring, and we know that the union is the same thing as 2 times the probability of the intersection. So we gave you kind of this like crazy formula piece here. And then from that, they want us to find the union, they want us to find the complement of the union, and they want us to find A intersecting with the complement of B. Again, there's no storyline to this. We can't even try to problem solve our way through it. We just have to brute force. So what we do know, though, is since I give you this here, we just had that formula written down. So you want to start with that. So the probability of A union B equals, so we're just writing the formula, the probability of A plus the probability of B minus the probability of its intersection.
Yeah, I do have a question.
So with this formula that you already know, you also just learned this piece right here. This was information that they told you. So what you end up doing with some of these problems is you look at what did they give you and what do you need. So they gave you this, so you wrote down that formula. We know that that is equivalent to that, so just substitute it in. 2 times the probability of the intersection equals the probability of A plus the probability of B minus the probability of the intersection. So again, we're substituting in what we know, because now I'm going to start to use the information that they tell us. I just start to put in, so I know the probability of A is 9/20. I know the probability of B is 3/10. And then I have this side here and this side here. Do you notice anything about those two things? They're the same, yeah. So we can say let X equal the probability of the intersection to try to make this problem simpler. You don't have to use substitution. You can make it U if you want. But we're just doing some kind of substitution to make the visual representation a little easier. So again, instead of this statement, we're going to call that X. Instead of this statement, we're going to call that X. So therefore, 2X equals that minus X. And now I have a regular plain equation that I know how to solve. Get your x's on one side, your non-x's on the other side. You're absolutely going to need to get common denominators, but we're trying to solve for X, which is the intersection. So I'll add that X over, so we get 3X equals, common denominators are 20s, so that's 6/20, 15/20, which you can reduce. 3/4, yep.
I wrote it upside down. Like, I wrote it correctly.
You got to get X by itself, so get rid of multiplying by 3 by dividing by 3. So I'm going to divide both sides by 3. Dividing by 3 is the same thing as multiplying by the reciprocal, which means X equals 1/4. So now I solve for X. X was this. So we just solved for X, and that was 1/4. So therefore, 1/4 equals the probability of the intersection. So that is my intersection, not my union, but that's my intersection. But what that does is it helps me fill out my Venn diagram. You guys are going to do a ton of Venn diagrams. So this is event A, this is event B. I found the probability of the intersection. Where does the 1/4 therefore go? in the center. And I know the probability of A. This whole thing is 9/20ths. So I have to get rid of 1/4. So if I'm going to get rid of 1/4, that's 5/20ths, which means I'm left with 4/20ths, which means this part here is 1/5. Because again, I knew the whole probability of A. Probability of B, that's 3/10. I have to take away 1/4 to figure out what's left. So 3/10 minus 1/4, get a common denominator of 20. That's 6/20ths and 5/20ths, which leaves this part of my circle for 1/20th. So now if I know all of these three circles, what do I know, how much, this is probability, how much is in the whole rectangle? So if I add them together, I'm just going to get these three, but in probability, what's the outermost piece plus these three? 1. Because one of these has to happen. If this doesn't happen, and this doesn't happen, and this doesn't happen, then it's the outside piece. So I have to add these guys up. So 1/5 plus 1/4 plus 1/20th, and I have to subtract that all from 1. Because again, probability, it's if I'm doing a Venn diagram, every single possible thing that can happen has to be in there. So therefore, if it's not one of those three parts of the circle, then I have to subtract it from 1. When I do that, I'm just saving the time. It's a half. The reason I found all of this information is so I can actually answer these questions. Okay. So now I can go through probability of the union, probability of this with the complement, the probability of A intersecting B with the complement of B. So I'm going to have you guys try this on your own before I just tell you what to do next. Okay, so the probability of the union. If I want to find the probability of the union, I add up these three circles. So the moon shape, the intersection piece, and then B's moon shape. Because that's union, is those things happening, this or this. So therefore I add them all up, and I end up getting 1/5 plus 1/4 plus 1/20th, and that is just 1/2. This one, it's not ideal here. This is just saying the complement of A union B. So what it's saying is it's everything but that piece right there. So that's the outside part that we just found, which just so happens to also be a half. It's never going to be the same like that. Very rarely is this going to be a 50% chance. So then the last part is A intersecting with the complement of B. When you guys get these, draw yourself out Venn diagrams if you need help seeing it. So this is saying A intersecting with the complement of B. So what I'm going to start with is what's the complement of B. So complement of B is everything but B. So it's the outside piece, that's not B, and it's this half moon shape in A. That's the complement of B. So now what I want to do is I want to intersect that with A. So when I intersect that with A are these two pieces here, right? That whole thing is A. I'm wanting to know where they intersect, and therefore they intersect in this region right here. So that was, when you look at your answer here, that is 1/5. Do shadings. Draw Venn diagrams on your paper. I will look for them. I'll look to see that you're doing the complement or not. Like I'll check to see if these numbers are right. It gives me a lot of visual help. So the next property that we learn about is dealing with mutually exclusive. We have to be really careful about assuming if things are mutually exclusive or not. So a lot of times we will be able to find if they're mutually exclusive based on information. Other times they will tell us, but what it means for two events to be mutually exclusive means they do not share anything. They do not share anything. So if I'm looking at what's the probability of me eating pizza and going for a car ride, they don't overlap. There's eating pizza, there's going for a car ride. There's nothing that they share. If I'm looking at picking socks out of a drawer, My socks might be red and blue. So I have some socks that fit in the middle. So those are not mutually exclusive because I could have a sock that's both scenarios. So if I'm looking at picking a red sock or a blue sock, there are going to be some socks that are red and blue. So we have to be really aware of what mutually exclusive is. So if they're mutually exclusive, what that means is there is zero intersection, and the addition rule, like what we just did, all we have to do is add their two probabilities, and that's it. There's nothing to subtract out because they don't share anything. So in this example, we're assuming the ties that we're picking are mutually exclusive. So Arthur has a drawer which contains ties. He picks a tie at random from the drawer. The probability that the tie is blue is 5/12, and the probability that it's red is 1/3. What is the probability of Arthur picking out a tie that is neither blue nor red? So what I want you to do is just take a minute here and figure out what's the probability of that occurring. So to start a problem like this, again, you have to know whether it's mutually exclusive or not. So we look at each individual probability. I want to figure out what's the probability of picking a blue tie. What's the probability of a blue tie? 5/12. And then what's the probability of picking a red tie? So list those things out. Always list out your probability statements. So we know those are each of the probabilities. Now, I want the probability of neither of them happening. So that's a little bit on the harder side to do. So instead what I might do is maybe instead of doing neither, maybe I figure out if it's either. Because if I want the probability that it's either, that would be the probability of B, and then what is going to go in the middle of them? The U. What is the probability of B union R? Which means I want a blue or red tie. So if I want to find the probability of blue or red tie, what do I do to these two probabilities? We add them up. So 5/12 plus 1/3, yep, which is 3/4. So now instead of one of them being red or blue, I want the probability of them not, which means I want to find the probability of this complement, which is 1/4. So now we are going to be working through some investigations, and this is just going to take some time to answer the question. So what I want you guys to do is you're going to start with investigation number 5 and go through. There's a Venn diagram, there's a two-way table in there, and I just want you to start working through that information. Then we get to a 6-sided die. We're going to be collecting some information. And then lastly, we're going to be looking at a spinner. So these are 3 different, very typical types of probability questions. So what I want you to do is I want you to start kind of thinking through, trying to answer them. Step 1, step 2, step 3, fill in that stuff. And then I'll come back through and I'll quickly fill stuff in for you. Does that make sense what I want you to do right now? Okay, so go ahead and do that on that. So we have 1 person that plays both, 2 that only do archery, and 7 people do badminton. So that wording can throw people off and make sure you want to put 7 here, but it's a total of 7, especially because here they said 2 only do archery. So they were kind of like breaking this one down for you, trying to trip you up on this. So this is using your Venn diagram, but there's also a really handy way of using a two-way table. Two-way tables can be super helpful for organizing your data because one person plays badminton and archery. Badminton and not archery would be 6, not badminton but archery, so archery and not badminton, that's 2 of them, and neither of them would be 3 because there are a total of 12 people. So then I can total these columns up, which makes probability go super fast. So then the total number of people who play badminton is 7. Total number of people that don't play badminton is 5. Total number of people who play archery is 3, and total number of people who do not do archery is 9. When I add this up and this up, I should get 12. That's the nicest thing about a two-way table is it should always add up to the total number of people. Total should be 12, correct. Okay. So again, that's called a two-way table. Then you can quickly answer questions. Find the probability. So now we bring in probability. So understanding when are we doing numbers, when are we doing probability based on what they're asking for. So this one is probability. So find the probability that a person chosen at random does only badminton. So then I look at this, and then the people that only do badminton, which means they do not do archery, that's 6 out of the 12. So then the question is, which of these, in your opinion, representing the 12 people in the sample space, is preferable for you? Do you like the Venn diagram, or do you like the two-way table? Two-way table? Anybody like the Venn diagram?
I think the Venn diagram is easier for me, but it's easier to find.
So now the next very typical type of problem is with sums of dice. So we have 2 die, we're rolling both of them. And this here is the sample space. These are the different outcomes that can happen. So what you end up doing is you organize your data in this. So in order to do that, what you need to do is you need to list out all your possible outcomes. Because they said here, for instance, one possible outcome is a 3 on the first dice and a 5 on the second. So 3 on the first dice, 5 on the second, they write it as 3, 5. So if you haven't done so, please fill this in. So now that we have it filled in, now we want to highlight all the different ways of getting a total score less than 6. So when you look at less than 6, so we're going to sum them up. Oh, let's change that to a lighter color so we can see them. Sum them up to less than 6. Can I include 5?
Yeah.
Is that less than 6?
No.
Nope. So inequalities are going to be super important, so I cannot include that one. Less than 6, less than 6, less than 6.
I was looking at there. Are you trying to write on the screen?
So
Okay, that makes sense.
with that in mind, now we can answer questions such as, what is the probability of scoring less than 6 when 2 fair 6 dice are rolled? So how many different ways can that happen? 10 out of 36, which of course you will simplify into divided by 2. So 5/18. So in this case, what's an advantage of doing a sample space diagram instead of just listing every possible outcome out? Saves time. What else? It's organized, so you're less likely to miss some. So sometimes a list is great. There's not a ton of things. You just list all possibilities. That's great. This one had 36 different possibilities. The last thing you want to do is miss it. So if you list all of these out in a nice organized fashion, it definitely is going to help you with that. However, what's the downfall to it? It's kind of time consuming, right? If you can visually think about it, sometimes that'll definitely help you with it. Okay. So the last one here, now we have a fair spinner with the numbers 1, 2, and 3. So spinners are the third most popular thing that you're going to see. We want to find the probability that the score on the last spinner is greater than the score on the first 2 spins. If I want to find the probability that the score on the last spin is greater than the score on the first 2 spins, how might you collect that data? What might you do? So what I want you to do is I want you to list out what all the different outcomes could be. Again, you're spinning a spinner 3 times, and the numbers that can come up on it are a 1, 2, and 3. So list out all different ways that that spinner could come up. So just do that. I think underneath problem part 8 there, I have some space. List it there because it's going to take you some time. So one possible output could be she spins a 1, then she spins a 1, then she spins a 1.
Yeah.
The next possible output could be she spins a 1, she spins a 1, then she spins a 2.
The next one will be 1, 1, 3.
Yep. And then you just keep listing all possible outputs. So one of the keys to writing out every possible outcome is you can't miss any. So you have to be smart about what you're doing. You can't just randomly pick, okay, I'm going to do 1, 1, 1, then I'm going to do 1, 3, 1, then I'm going to do 1, 2, 3, and like you have to have some kind of pattern as you're going through, no matter what the case might look like, so you don't miss any of them along the way. So question number 3 is, how many possible outcomes are there? Did you count? There are 27 for this situation. There are 27.
Too many outcomes.
So when listing outcomes, you need to be systematic, otherwise you're going to miss some. So circle those outcomes in your list in which the last spin is greater than the scores of the first two spins. Let me say that again. Circle the sets of outcomes in your list in which the last spin is greater than the scores of the first two spins. So can I use this at all, this column at all? No, because this column all starts with 3s, so there's no way any of those last digits are going to be bigger than a 3. So then it's just these two columns, and there are a total of 5. If you were going to do a sample space diagram, like we did with this one here, what would have to be true about it? So we're looking at what would it look like, because guys, it's impossible. It has to be three-dimensional. It's not a two-way piece, it's a three-way. The only way I could look at spin 1, 2, and 3, if I were going to try to organize it, I would have a cube, and I would have the length, the width, and the height to represent all possible scenarios. So there's no way you are going to create this, because this only has 2 different independent variables. The one that we just did has 3. So this is like your x, your y, and then we have to pull it off the paper, and that's our z value. So a sample space is great because it helps us organize it, but in this situation, it's impossible unless you were somehow able to draw it three-dimensionally. So there's pros and cons to each of the different pieces here. So why do we not draw a sample space diagram? Because it's three-dimensional. So now, answer these 2 questions, please, for 7 and 8. If we would not have listed all of these out, how easy is problem 7? No. Like, you wouldn't be able to keep all these straight in your head unless you list all of these out. But once we did, we could very quickly see there were 5 of them. We found out there were 27 as long as we didn't miss any. So therefore, the problem is a nice, straightforward, probably 3rd grade math probability question, 4th grade math probability question. But this is the part that's tough because you've got to keep track of all of your different scenarios. So in question 8, we're asking what are different ways to organize your sample spaces? Because the problem with this is I am going to give you a problem that says this, and you need to know what to do. We're not going to say, do this, do this, do this. You need to know how to do that. So therefore, the last part of this question is asking, when you get something like this and you need to see your sample space, what are different ways that you can organize it? So we just did this. This is just a list. What else could you do?
Maybe all the ones that have 3s, just like as the previous value.
But like that's still listing them out. So what's another way of organizing things, just in general? A Venn diagram, yep. How else could we represent our information? The chart, the probability space diagram. So being able to physically see it. Okay, two-way tables might be helpful with information as well. That's another way to do it. Because again, I'm not going to tell you what to do for these problems. All 3 of these are very traditional types of problems. This was one of the questions. Let's see, where's this one? This was one of our questions. And that's it. That's all we're going to tell you. And you need to know what you have to make, what you have to see, so that you can answer those questions. So in this last one, I'm not telling you too much other than the following. In an experiment, a coin is tossed and a 6-sided dice is rolled. Make a diagram for the experiment. I'm specifically saying a sample space diagram. And then I want you to find the probability that a single experiment you obtain a head and a number less than 3 on the die. So this is your way of organizing it with a sample space experiment. So because there was just 2 pieces of information, one goes on one axis, one goes on the other. It doesn't matter which way you order it. You could have done vertically the 1 through 6 and horizontally heads and tails. It doesn't matter a bit. However, in this problem, we wanted the probability that a single experiment you obtain a head and a number less than 3. Had less than 3, had less than 3. Therefore, what is the probability of that happening?
2 out of, or,
Which simplifies to
um,
1 second.